let's gain some more practice and experience creating our own custom estimators. So for the California housing data, one of the things you realize is two of those characteristics, two of those attributes for our data set are the latitude and longitude. Now let's do something with these two features. Let's somehow combine them and generate a third new feature based upon these two. And we understand that when we're dealing with housing prices, location is something very important. So let's generate a feature that tells you how far away you are from LA. Notice we have data for a census block in California. Let's generate a metric, a distance, telling you how far a census block is from Los Angeles and San Francisco. In other words, let's say we have a census block right here, and this is the city of LA. We want to figure out what is this distance. This distance right there. And same thing for San Francisco. So I know it's not completely drawn on a scale, but we would want to do the same thing for San Francisco. Or really for any city. So here comes our data. And one thing we want to do is we want to go ahead and have some sort of transformer step. And here we'll return the dist from LA. But we also want to do it for San Francisco. So our data must go through these two transformer steps that are acting in parallel. So think about what tool we will use in scikit-learn to combine these two features. We will have to use feature unions. But let's not worry about using feature unions at the moment. Let's go ahead and construct this transformer. We want to construct it to be as general as possible so that any user can take this transformer, plug in a different set of coordinates that represent a different city or different point on the map, and calculate the distance. So let's not hard program the coordinates for LA and San Francisco. Let's make just a general transformer that we can reuse for different cities. So let's go ahead and do that. Let's go back here. Okay. All right, so let's go ahead and define our class. So I'm going to use the camel case. So I'm going to call it dist from city. It's going to inherit the base estimator and the transformer mixin. Okay, since we have a transformer. All right. So let's go ahead and define the init method. So let's consider what are any parameters we want to pass when we construct an object from this transformer. And since I said before, we want to make sure this transformer is as general as possible. So when we construct an object from this transformer, from this class, we should pass it the coordinates that we're going to use to calculate distance. So here we want to pass the coordinates. So the question becomes, what data structure should we use to pass these coordinates? Should we pass them individually? Should we do something like lat and long? Pass those two separate ones, or should we go ahead and pass it as just one, using one data structure, like call it coord? It's a bit of a matter of preference, but I'm going to say let's just pass one value, one object. So this coord must contain both the latitude and longitude for the reference city. So what would be a good data type for coord? Well, a good data type for coord would be something like either a list or a tuple, something that has order. Using a dictionary is going to be a bit overkill. We're only holding two values. And when we work with coordinates, there's a strong convention that the first one is the latitude and the second one is the longitude. So this coord is going to be some data type of a list or a tuple. So let's go ahead and define coord for our object. So we do self.coord equals coord. So when we create an object, it will have an attribute called coord, which will be equal to whatever value we passed it when creating the object. So we have the init method defined. Let's go and move on. Let's define the fit method. Let's talk about what's going to go on the fit method. What do you think should go on the fit method? Well, the fit method, if we recall, this is where we're going to put anything we need to calculate for our transform, any values we need to calculate for the transformation process. Is there anything we need to calculate for our given data set? Any parameters we need to calculate beforehand before we actually apply the transformation? Now there isn't anything for this situation. There's nothing that we need to do during the fit method. Of course, it has to have this fit method. We need to define it. So we're going to have a very empty fit method, an empty fit method. So we still have to go through, define these things. So we say x, we're not going to use a label, so y equals none. Okay, and we're going to say return self, and that's very important there, return self. We want to make sure that all the fit methods of all the estimators are always going to return self. In fact, later on, let's go ahead and we get everything running. Let's remove this and see what happens and see the error message so we can identify when we see this error message when we're working on something else. We've seen it once, we can go ahead and know exactly what is the problem. So we'll make that error later on. Alright, so the next one is to define the transform method. Transform self.x. Alright, so here is actually where the transformation occurs for our estimator. Okay, so one of the things we got to do is we got to pull out the latitude and the longitude of our feature matrix of x. Now one of the things we're going to assume here is we're going to assume that that only the relevant columns go into this transformer. Our data set, I believe, has 8 columns, 8 features, 8 characteristics for all our observations. We only want 2 columns to go into this transformer. So we're going to assume that this only has 2 columns, and that the first one is the latitude and the second one is the longitude. So let's define the transform. So I'm going to call one column the latitude, so the first column. So do bracket colon 0, 1, so this is NumPy. So we're working with a NumPy array. So we're saying give me all rows but only the 0 column. That would be the latitude, and the longitude would be all rows, column number 1. Then from here, let's actually start calculating the distance. So the formula is just a distance. It's just a simple distance formula. So I'm going to say lat minus, now I've got to subtract the latitude of our city. Remember where that was stored in? Where we stored that? That was stored in this coord variable when we created the object. So let's go reference it, do self.coord. And notice this coordinate is going to be, I can type here, some list or tuple, where the 0 index represents the latitude. So we'll just put self-coord 0, so that's the latitude for that city. We're going to make sure we square these values. Square them there. Then let's add the other part, so the longitude minus self.coord of index 1. So that's the longitude for our city. We square that value. Since this is all a NumPy array, we're going to use a NumPy square root function to calculate the square root. Let's go ahead and do that. So there is our distance. Okay. Now let's go ahead and return dist. Let's prototype this. Let's go ahead and actually run this, see how well it works. See any things we got to do. Okay. So I'm going to say dist LA. Let's create an object from this transformer. Let me just back up. Let me define a variable called coord LA. So it's 34, and this is roughly, I can just look this up in Google. Go ahead and do this. Say LA coordinates, see what we pull out. Okay, so it's 34 north and then 118 west. So we don't have to be too precise. We can, be very precise later on, but we're just trying to get something to work. So I'm going to say 34 and 118. So I had that correct. And notice that since this coordinate is 118 west, I've got to make sure that it is negative there. Okay, so let's go ahead and find the dist from LA. So dist from city, we pass the coord LA. Tuple I defined. Do list.la, dist.la, and just do fit and transform. Do it all with one step. I'm going to pass x. And let's see, of course, just fix this up. Back up and create a cell here. Okay. So if I go back to the description, let's see, print, what I call it, data, dscar, description, in that order. So the latitude and longitude are the last two columns of our data set. So I make sure when I pass here, I'm going to say, give me all rows and the last two columns. Let's take advantage of negative indexing. Okay, so it says invalid square root in path. Let's go back here. Let's see what mistake I did there. Just make sure that indeed the last two columns or my latitude longitude. Okay. All right, that makes sense. Okay. Trying to find my mistake. Bear with me here. Something is going on where once let's just redefine things here. Yeah, so we're getting not a number. So it's trying to square root something that doesn't make sense. So if I look at x, okay, those should be all my relevant entries there. Must have made a mistake here. there's my mistake. I'm squaring. Yeah. Issue there. Sorry about that. Thank you for your patience. All right, there she were. All right, so now we have all the distances between the census block and LA. All right, we got that to work. Let's move on. Okay, but notice the output. Notice the shape of this output. The shape of the array. Let's figure that out. Let's say dist equals fit and transform. Run that. Let's look at our array. So it's just one-dimensional array. But we got to make sure that any of these features we generate has 2 dimensions, has rows and columns. So we got to go back here and just reshape it. So it's be dist equals dist reshape. Just reshape it. So however many rows are required if we want to reshape it to have 1 column. So go ahead and run that. Run this cell here. Let's look at the shape. And there it is. All right. That's what we want there. Okay. So notice what I did here is I had to manually drop certain columns that are not required for this transform, because in this transform we are assuming that the first 2 columns, 0 column and the 1 column, represent the latitude and longitude respectively. Now I don't like this dropping this thing manually. It's a bit cumbersome. We have to remember to do it every time. So let's create a custom transformer to do this dropping for us automatically. So let's go ahead and do that. Class drop columns. So base estimator, and the transformer mixin. Define the init method there. And here we're going to pass in this init definition the columns that we want to keep. So we say self.end calls equals end calls. Self none. All right, just return self there. And during the transform method, let's go ahead and use those defined end columns to do the dropping. So we're going to return X. We're going to return all the rows. We're not going to drop any rows, but only keep the columns defined in end calls. No longer need that. Okay, no longer need that either. All right. So what's going to happen here in my process is here comes the data, all 8 columns. It's going to go to this drop. It's going to drop all the columns except for the last 2 and calculate the distance. So it's a dist from LA. But I also want to do that as well for San Francisco. Do the same transformation process, but just for San Francisco. So it's a dist for San Francisco. And I also want to make sure that I include my original features, the 6 original features. So in this drop of my original features. So it's going to drop the last 2, keep the first 6. So I want those included into my data set. So one way you're viewing about this transformation process is that we're taking the latitude and longitude of our original data. We're going to do something with them. We're going to actually generate distances with them. Replace them with these distances, and we want to make sure we keep the original ones, and then we're going to feed it into some predictor there to make predictions. So this is our workflow process. So it makes sense that we want to encapsulate this 2-step process using a pipeline, this 2-step process using another pipeline, let's combine this here using, guess what? What type of tool will we use to combine these 2 pipelines, these 3 steps in parallel? We would use a feature union. So we're going to encapsulate this using a feature union. So now it's 1 step. We want to make sure we combine everything into one grand estimator, and that's going to be wrapped around here. So hopefully that makes sense. Let's go ahead and start doing it. Okay. So I'm going to define a, say, okay, let's go ahead and define my dist LA. Defined that before. You just keep on adding here. Let's do San Francisco. I looked those up earlier, and I believe it's 37 and 122, negative 122. Okay, so define dist of San Francisco. So notice the importance of making our transformer as general as possible, because we can just add other sets of coordinates and it would work just as fine. Let's define our drop. So drop columns. In this case, we're going to drop 0, 1, 2, 3, 4, 5. So keep 6 and 7, index 6 and 7, so the last two rows. Our drop column. Let's go ahead and do union. Let's see, do I have, yeah, I've imported feature union. So in there, one of them is going to be the drop. It's going to be LA. I'm going to call this step LA. It's arbitrary, but let's name something that is noteworthy. San Francisco. Dist SF. Okay. Okay, dist LA. Okay, let's see. Let me just look at what I have here. Everything is set. Okay, let's do a pipeline. Pipeline. We have here our union. Then we have our regressor step. And there, we'll just use simple linear regressor. We just want to prototype this. Nothing fancy there. Let's pass our data set. All right. That seems to work. And pass x and y. Let's see if we can derive a score. So that works. The score method works. Things seems to be working fine. And pipe.predict on x. And we get our predictions. All right. So that seems to work all fine and dandy. So a couple things I want to emphasize is, notice here, we made the choice, so let's make this as general as possible, work for other cities. So that's important. Let's not hard code. Let's not create a custom transformer only for LA and a custom transformer only for San Francisco. We're going to repeat code if we do it that way. Let's make it general as possible. It can work for any set of coordinates we pass it. We also had to decide what will be a good data structure to store these coordinates. We could have stored them as just integers or floats, individual one for the latitude, individual one for the longitude. But I would argue it makes more sense to store it as a tuple or some sort of list. And notice we had to invoke this drop columns to make sure that into this transformer we only include the relevant fields, the relevant columns, the latitude and longitude. In this case, we exploited that we knew the order. We knew the order of our feature matrix. We knew where the latitude and where the longitude was located. But perhaps if our data came up in a different format, let's say our data was in a pandas data frame, then we could have exploited the name of those columns, so perhaps a little more readability. So we could have had a transformer up in front where we would select certain columns, select certain select certain columns over a pandas data frame by passing the name of those columns. Like I said before, sometimes it helps to sketch out what's going on in the process diagram when we implement our workflow.